Okay, well, we're only missing 5 people, so I guess we can get started. So, just a reminder, test 2, still a ways away. And I've updated the site to reflect the change. And it's going to be on all of everything covered in chapter 14, which I'm still working my way through. So, we'll see. I'm going to get through a couple sections during this shortened week, and then we'll finish off the chapter next week. So there'll be plenty of time to get the homework done, and then use that to be ready for the test.
Did you say everything up to 14, like 13.7?
Oh,
to present.
Actually, I've already made up the test and a practice test, and I kind of forgot to put a Lagrange multiplier problem on there. So, and there are too many problems with integrals. Now, I still reserve a right to include one on the final because the final is comprehensive, but at least it's just one problem out of many instead of a huge chunkier grade. So,
if you want to add a bonus problem on there, that'd be great too.
I will consider that. So, practice test is up on the lectures page under the November 4th entry. I don't have this. I just did it this morning, so I haven't written up the solution yet. But hopefully, sometime this week, I'll have that accompanying it. So we still have a ways to go in this chapter. So when you look at a practice test, if you were to do it right away, certain things. Actually, after this week, you'll be able to do everything except the last problem, because that's on the general changes of variable, which we haven't got to yet. Okay. So, and keep in mind, it's just indication of the types of problems you will see. Don't read too much into it. Well, like as far as the specific, basically, you're going to spend the whole test evaluating integrals. That's it. Just integrals of different kinds. There's double integrals over rectangles for more general regions. There's triple integrals. There's using polar coordinates. And I'm going to look at 2 other coordinate systems today. And a lot of it will be about how do you set up the integral. That's a significant part of the point. Okay. Now, with the number of homework coming up due, does anyone want to ask about that? I think it's 14.3 that is out there now. No questions on it at all? Or how many have not started yet because it's not due until tomorrow? Okay. I appreciate your honesty. Okay. All right, well, I'll get to the new stuff, so then if any question comes to mind, maybe we can make some time toward the end of class. All right, so we have cylindrical and spherical coordinates. Might not get through the whole thing today, but we'll see how it goes. Okay, so this is, I'll have my browser going in case somebody does have a homework question later. Okay, now, in double integrals, we saw that we could change into polar coordinates and possibly make them easier. So now we have 2 options to extend polar coordinates to 3D to help evaluate triple integrals. So first I'll introduce the coordinate systems. So both of these generalize polar coordinates from 2D to 3D just in different ways. So the easiest way to describe polar cylindrical coordinates is polar plus z. So you describe x and y in polar coordinates like we did before, and then z still remains z. So really you're only changing two of the variables, not all three. So then going back to cylindrical from xyz, we have r as before, tangent theta is y over x, and then z is z. Cylindrical coordinates is what you'd want to use if the expression x squared plus y squared comes up in the description of a domain or the integrand. So that's kind of your tip-off that you might want to do that. Now with polar coordinates, and I'm using highly non-rigorous terminology here, but I figure it's what would stick better with you guys working with problems. So in polar coordinates, we had to throw in an extra factor of r in your integrand when you're converting. And the same is true for cylindrical coordinates, because it's only this really is polar coordinates all over again, just with an extra z dimension that isn't going to change anything. Okay. So to make sense of cylindrical coordinates, if I were to draw a cylinder that was centered on the z-axis, r is the distance from the z-axis to the outer edge of a cylinder. And the if I were to pick a point out here somewhere, well, here's the x-axis. So the angle that this point makes with the positive x-axis, if you were to project everything down to the xy plane, whoops, z doesn't go there, z goes up here. That would be theta. So it has the same meaning as it does in polar coordinates, and z has the same meaning as before. Okay, now spherical coordinates generalize polar coordinates to 3D in a different way. So first, to visualize, whoa, that's awful. This is supposed to be a hemisphere, believe it or not. Okay. Now, just as in polar coordinates, r represents distance from the origin. That's no longer true in cylindrical because it's only distance for x and y. Here we have a three-dimensional distance, so rho is distance from the origin to a point. So I have rho is equal to square root of x squared plus y squared plus z squared. All right. So it plays a similar role as r in polar coordinates. Now, if I draw another point over here, and then I project it down to the xy plane, theta has a similar meaning as it does in polar coordinates. So if you were to take whatever point you have and just project it onto the xy plane, or set the z coordinate equal to 0, and see the angle that the point makes with a positive x-axis, that's theta. So just like in polar coordinates. So because we're in 3D, we need an additional angle, phi. And I'll draw a side view. So this will be like the x and y plane, and then the z-axis is still going up and down. So here's your point. In this projected view, you can't see what theta means, because that's only going on the xy plane. Okay, so rho is your distance from the origin, and then this angle, phi, is called the angle of inclination. So it's the angle that the point makes with the positive z-axis. Now, theta converts in a similar way as in polar and cylindrical coordinates. Tan theta is y over x. That's no different. Now here, if we were to use right triangle trigonometry, so we have z going along here, like this distance, and then phi is the angle. Using right triangle trigonometry, what you would find is that cosine of phi is equal to adjacent over hypotenuse, z over rho. So that's how we can convert from x, y, z to rho, theta, and phi. Now, theta goes from 0 to 2 pi, just like in polar coordinates. But phi does not. Phi goes just from 0 to pi. Now, as phi varies from 0 to pi, there are really three angles of interest. So when phi equals to 0, then the point is on the positive z-axis. So you can think of that as North Pole. So with that in mind, what angles for phi, and you can use a picture to help, would correspond to like being at, if this were the North Pole, what would be like the equator or South Pole?
Pi over 2.
Yeah, pi over 2 would be the equator. And then the South Pole? Yeah. Okay. So from a description of a problem, like whatever integral you need to evaluate, if the description indicates that the domain is only contained in the upper half space, like from z equals 0 on up, that means that your phi limits would likely be just from 0 to pi over 2. Okay. Now, because here's how we convert from Cartesian to spherical. How do we convert from spherical to Cartesian like this? So we have x is equal to rho cosine theta. So that part is similar to polar coordinates. So then we have sine phi, and then y is equal to rho sine theta sine phi. And then z is equal to rho cosine of phi. So notice z doesn't depend on theta at all. Now, anyone here is a physics major by any chance? Okay. Yeah, physics, they tend to reverse theta and phi. So when I teach a class that, like Math 415, that's required for physics majors, and of course math majors take it too, it's a recipe for confusion. Okay, but we're in math world now, so I gotta stick with this convention. Let's see. Oh, get the attendance taken care of. Okay. Now, actually, if you look at the picture, okay, so this is, so this side of a right triangle is rho cosine phi. So rho sine phi is equal to this distance. So in fact, what you can say, and what is this? This is a distance from the point to the z-axis. So this is kind of like the r in polar coordinates. So in fact, I could say x and y is equal to r cosine theta, r sine theta, where r is equal to this rho sine phi. So that way you can see there were similar relationships among the variables in spherical coordinates to what we see in polar and cylindrical coordinates. Okay, now what about the extra factor? It's not the same. It is rho squared sine phi. Right. So definitely keep your angle straight. Don't get your thetas and phis mixed up. That's definitely going to cause a point loss. So keep straight which coordinate system you're dealing with. Polar versus 2D versus cylindrical versus spherical, and what do you have to include in your integrand. So if you took a rectangle in spherical space, like a rho, theta, and phi, all bounded by constants, and then you map that using these equations to x, y, z space, what would the volume of that be? That's the volume. So that's why this extra factor needs to be included. All right. So these are the two coordinate systems that you'll need to be familiar with for triple integrals. So now what I'll do, I have some examples of each. Okay. Oh, by the way, I think it was last Friday or recently, someone who was here in class did not sign the attendance sheet, so make sure you don't get missed. Okay. All right, so first we'll look at cylindrical. Now, this example is just going to be a setup problem. Okay, so E is going to be a solid, so it's bounded by a paraboloid. Z is equal to x squared plus y squared, which we've seen in other examples. Also, it's bounded above by z equal 4. And also the planes y equals 0, y equals 2. So for instance, if f of x, y, z was equal to 1, then we'd be computing the volume of this solid. So to get an idea as to what the limit should be, when we switch to cylindrical coordinates, all right, so here's the paraboloid. And then you have this plane that marks the top of it, that cuts it off at z is equal to 4. But we're also looking at, okay, this is x and this is y. So y equals 0 is a boundary. And then also, this plane y equals 2 is a boundary. So that's cutting into the paraboloid. Okay. Now, if we were to write this as just an iterated integral sticking with x, y, and z, now, so if we look at this, x squared plus y squared equal to z, but z can only go as high as 4. So, so if we were to, so how big is x squared plus y squared? If that can only go up to 4, then how big can x and y possibly get?
2.
Yeah, so if you were to look at this from above, the paraboloid would look like a circle, and that circle is only going to get as big as radius 2. So we'd have x squared plus y squared is equal to 4. So basically what you're doing is you're setting these equal to each other to see how big certain variables can get. So if I want to do this as a integral of, my outer limits would be an x, and they would be constant. So what limit should I put here? Yeah, and then you're bounded by y equals 0, and then it turns out the bound y equals 2 is kind of moot because the circle doesn't go that high, doesn't go past that point anyway. Okay, but this y equals 0 is a boundary, so anything below that you're going to ignore.
Y goes 0 to 2.
Yeah, y goes starting from 0, and then how high would y go? What would the upper limit be? Well, again,
X squared. 4 minus x squared.
almost.
Square root.
Square root, yeah. Square root of 4 minus x squared, because you take this equation, we're looking at y limits now. So you solve it for y, and we want the positive square root because we're only focusing on where y is positive. And then finally we have the z part, but that's given away by these equations. The lower boundary is the paraboloid, so that would be x squared plus y squared. And then the upper boundary would be the plane, so 4 would be the upper limit. Now, this doesn't look like a very pleasant integral. And how bad it is would depend on what f is. But let's take a look at cylindrical coordinates. So then we will have limits in, whoops, I don't want to do that yet. So you'll be substituting, x would be r cosine theta, y is r sine theta, and then z remains z. And then you have your extra factor, r dz, dr, d theta. So what would the limits be, for instance, for theta? No, it's just like polar coordinates.
0 to pi over 2.
0, yes, but not pi over 2.
Pi.
Yeah, pi over 2 would only take you to here. Pi gives you the entire upper half of a circle. Okay, and what about r?
Negative 2 to 2. No.
0 to 2. Yeah, because we're looking at distance. It's going from the origin radiating out up to this point. And now, the z limits would be similar to what you had before, except you'd have to express them in polar coordinates rather than Cartesian. So what is x squared plus y squared in polar?
R cosine squared theta.
But you're looking at the top coordinate system. Okay, so r squared. Yeah, because you'd be using this.
Oh.
Yeah, so you were looking down spherical, weren't you? Okay.
No, I was just looking at x.
Yeah. Yeah, and then 4 would be the top limit. So, okay, so at least we don't have as many non-constant limits as before. So then don't forget your extra factor, and then you can go ahead and evaluate from here. So any questions about how we get the limits for this one? Okay, so what you're seeing is, in every single example I do, I'm drawing this as best I can. And so it's a good idea to see the similar shapes coming up, paraboloids, circles, spheres, etc. Because you can't really get an idea as to what your region you're integrating over looks like. It makes it a whole lot harder to come up with the limits. It's not something that you can just memorize or otherwise infer from just doing a bunch of examples.
For dr, why did we use 0 to 2? I understand why we use 0, but why do we use 2?
Because r is distance from the origin.
So we
Oh.
don't use the square root of 4 minus x squared?
Well, no, because that's used to express y, and we don't have y anymore. Yeah, because now we have coordinates that have entirely different meanings, or at least for x and y changing to r and theta. Okay. Any questions? Okay. All right. Let's do another with cylindrical.
Are we gonna use the same numbers, the same column? To do cylindrical, we use the same ones?
Same. What is
Column,
it?
the same coordinates.
Okay. I'm still not sure what you're asking.
Are we gonna use this same diagram for the other?
Okay. I'm not clear what you mean by what being the same.
They
Okay.
just use the diagram, or we're going to use the same diagram.
Well, I mean, well, the same diagram we use for all over the place. The thing is, about shapes you would be including, then it would be different. Just because you'd be looking at whatever the description of your solid is.
That's what I was asking, we're gonna use the same thing to do the spherical.
Oh, well, it's the same general idea, but I'm hesitant about saying that something's going to be the same because there's too many possibilities for a problem to be different, and especially since I'm still unclear as to what you mean by something being the same as something else.
How we went from Cartesian and did the same thing for the cylindrical, I was wondering if we was gonna use the same thing and do the spherical using the same
Oh,
information.
like using this? No, because generally one coordinate system is more suited to a problem than another. Something that be made much easier by using cylindrical might be crazy to do using spherical. Yeah. Sorry, it just threw me off because I haven't never bothered looking at it that way. It's always a matter of, for a given problem, which coordinate system is the easiest to use. You just use it, and that's it. Okay. Okay, so x is our integrand, so that'll have to be converted to cylindrical. This is still cylindrical. So E is bounded by cylinders. So what you're accustomed to seeing as an equation of a circle in the xy plane is now a cylinder when in 3 dimensions. All right, so it's a solid contained between these two cylinders. So if we look at this from above, okay, and then also bounded by the planes, z equals 0, z equals x plus y plus 5. So so you have this ring between these two cylinders, but it gets cut off at the bottom by z equals 0, and then there's a plane up top, a slanted plane that cuts through it, x plus y plus 5. So we need to, so here are boundaries in Cartesian coordinates, and we can still use these for our z limits as long as we convert to polar. So our integrand is going to be r cosine theta, so that's x. Your extra factor of r, dz, dr, d theta, So these would be the z limits. So 0 would be your lower limit, and then your upper limit would be r cosine theta plus r sine theta plus 5. Because this is x and this is y. So whatever equations you have, you convert them to cylindrical coordinates, or at least you convert the x and y to polar coordinates. Now, if you plug in r cosine theta and r sine theta for x and y in here, you can also see what your limits for r would be. But it's faster, instead of doing that and trying to simplify, it's faster to just remember what x squared plus y squared is in polar coordinates. So what would the limits be for r?
4 and 9.
Got to take square root. Yeah. So this is radius 2, and this is radius 3. So 2 to 3. And then what about theta? There are no other restrictions.
0 to 2 pi.
Yeah, we're going to go all the way around. Because I didn't make any cutoff like a y equals 0 or anything like that. Okay, so we have unfortunately one set of variable limits, and everything else is a constant. Okay. All right. Now, okay, so now as far as how to evaluate this, so we can pull things out a little bit. Like we can pull a cosine theta out all the way to here. A theta integral. The r squared can be pulled out all the way to here. And then you've pulled out everything. So you have 0 to 2 pi in theta, with cosine theta sitting out here. And then 2 to 3 in r, with the r squared sitting out here. And then what's left would be 1, but that would just be the difference of the limits. So now we'd have r cosine theta plus r sine theta plus 5 dr d theta. So this is after evaluating the z integral just by taking the difference of the limits. Okay. Now, as far as continuing to evaluate this, it'd be best broken up into 3 integrals, because we have 3 terms, for r cosine theta, r sine theta, and 5. So by the time you break it up into 3 terms and pull things out as much as you can, you'd have 0 to 2 pi cosine squared theta, and then d theta, and then 2 to 3 r cubed dr. So that's coming from a first term. And then you have 0 to 2 pi cosine theta sine theta d theta, 2 to 3, again r cubed. And then for the last term, you'd only have 5r squared cosine theta. So you'd have a 5 that you could pull all the way out. And then you'd have 0 to 2 pi cosine theta. And then 2 to 3 r squared dr. So all I did to get from last step to here is break this up, break up the sum, so we have separate integrals, and then just combine like factors, and then when you have a function of r times a function of theta, then you can break it up into separate integrals like I have here. Is there any questions at this point? Now, to make things a little bit easier, and yes, you can use this shortcut on a test. If you have a function like sine or cosine, if you're integrating it over a full period, it's just going to be 0. So that's one thing that would come up now and then. It's just cosine or sine by itself.
What do you mean over a full period?
Cosine and sine are 2 pi periodic. So integrating from 0 to 2 pi or minus pi to pi. So if the whole interval fits in, basically eats up a period or multiple periods, as opposed to cutting off in the middle of a period, then you can say right away that the integral will be 0. So for instance, like cosine 2 theta from 0 to pi is also 0 because of a factor of 2 that cuts the period in half. The period's now pi.
Okay, I see.
Okay. Now as for these other ones, so you'd handle these other two very differently. Like for this, you can use u equals sine theta. So then du is cosine theta d theta. So you'd be integrating u and get u squared over 2. Whereas for this one, you'd have to use a trig identity. So cosine squared is equal to 1 plus cosine 2 theta all over 2. I am open to putting certain trig identities on the test, like a formula sheet. Okay. And then you can integrate that from there. Although what will happen is when you go to integrate cosine 2 theta, that part's going to be 0 because you'll be integrating over 2 full periods. Now, all of this is worked out page 95 in the notes. So you can see the rest of the gory details there. I'll make sure to do at least one spherical coordinates example. Now keep in mind the setup for each problem on the test, the setup is a significant portion of a point. So if you have your integrand and you integrate that perfectly, if it's not with the right limits, yes, I will give you some partial credit, but not as much as you might think. Okay. All right. So spherical case, we have so we're integrating over this function, x squared plus y squared over a solid h, where so it's bounded by the xy plane, so z equals 0. Actually, in my notes it says the xy plane, but it's important for you to recognize those are the same thing. And also by the sphere, x squared plus y squared plus z squared is equal to 1. So basically we're just integrating over a hemisphere, which I guess is why I called it h. Now, we're in spherical coordinates, not polar or cylindrical. So x squared plus y squared, you can't just say it's r squared. You have to express it in terms of rho, phi, and theta. But for convenience, if you keep in mind that x is rho cosine theta sine phi, and y is equal to rho sine theta sine phi. If you were to take x squared plus y squared, so you get rho squared sine squared phi, and then you'd have cosine squared plus sine squared, which equals 1. So it does simplify. You get rho squared sine squared phi. So you can either be prepared to work this out, or you could just remember that in case that expression comes up. Now, we need limits in. Okay, Okay, so our integrand is going to be rho squared sine squared phi. That's your x squared plus y squared. Then the extra factor, rho squared sine phi, and then d rho, d phi, d theta. So we need to figure out the limits for rho, phi, and theta and hope that they're constant. So since we're working with this hemisphere, now, what should the limits be for rho, for instance? Rho is distance from the origin.
Negative pi over 2 to pi over 2.
Looking at the wrong variable.
Oh.
Distance, not an angle.
Right. Whatever that top curve is.
Okay, but a sphere consists of all points that are a certain distance from the origin. These points that are on the sphere are distance what from the origin? 1. Take square root of that. Yeah, so 0 to 1. Okay. All right, so those are our innermost limits. Those are constant. Okay, theta.
0 to 2 pi.
Yeah, same meaning to polar coordinates. We go all the way around. And finally, phi, the angle of inclination. So we're only covering the top half. So this is where you remember your North Pole, South Pole, equator stuff.
Was that right the first time?
Half right.
Half right, okay.
Pi, 0, pi.
What would be pi over 2 to pi?
No.
Or are we just...
Yeah.
Okay, we're just doing like the top portion of the sphere, right?
Yes.
Okay.
0 to pi.
Both of you were half right, but
0 to 2. 0 to pi over 2.
yeah. North Pole is 0.
And then root.
And then pi over 2 is the equator. Okay. So now the integral is set up, and thankfully everything turned out to have constant limits. And because this integrand is a product of function of rho times a function of phi, and there is no theta, you can write this as a product of 3 integrals. So the integral of 1 d theta, and then integral of sine cubed phi d phi, and then integral 0 to 1 of rho to the 4th d rho. So you can break it up like that, and now you have 3 single integrals to do. And 2 of them are pretty straightforward, because this one you just take the difference of the limits, so you just get 2 pi for that one. I'll talk about this one in a little bit. That's the hard one. And what about this one?
1.
This
Just give me
one.
1.
What? No. 1/5, because you get
Sorry, yeah.
rho to the 5th over 5 with limits 0 and 1, so it turns out to be 1/5.
I forgot about the denominator.
Okay. Now, for this one, we need to do some rewriting. Sine cubed you can write as 1 minus cosine squared phi times sine phi d phi. So this is something you do whenever you have an odd power of sine or cosine. So this was sine squared. And now you can do substitution. U is equal to cosine, and du is minus sine. So now what you get is minus the integral of 1 minus u squared du, and the limits when phi is equal to 0, cosine is equal to 1, and then when phi is equal to pi over 2, u is going to be 0. So you get that, but what you can also do is I can flip the limits and get rid of the minus sign. and then you can finish off that integral from there. And you don't have to do it this way. You can also just go ahead and integrate 1 minus u squared, then change it back to phi and use the original limits. Okay, and this is, again, more of the details are on page 98 of a notes as to how that one is worked out as far as the Cal 2 parts. Okay. So any questions about this one? Okay, I thought I had another one. Oh, I did. I mistakenly skipped over it. Okay. Oh, whoops, forgot to. All right. So whoever's watching at home. Okay. Let's talk setup on this one. Of course, I'm missing one page actually. So volume of solid bounded by z equals 0. X squared plus y squared plus z squared equals 9, and x squared plus y squared plus z squared is equal to 16. Okay, and also the planes y equals 0 and y equals x. So if we look at this from above, we have a sphere, 2 spheres of what radii? 3 and 4. Take the square roots of these. Okay, so then your integrand would initially be 1, and then your extra factor, rho squared sine phi, d rho, d phi, d theta. So your rho limits would be 3 and 4. It's contained within those 2 spheres. The fact that we have z equals 0 as a lower boundary, what does it tell us about the phi limits? So we have, it's basically this thick dome is what you're integrating over. So again, North Pole, South Pole, equator. Zero to what?
We're looking for limits of rho.
No, rho is 3 to 4.
Oh, okay.
Phi.
That was very confusing.
Yes, pi over 2. And finally, y equals 0 is a boundary, and y equals x is a boundary. That affects your limits in theta. So give me the limits to theta, and we're out of here. It's this part right here. So between here and here, what angles are those? So, what?
Pi over 4?
Yes, pi over 4 is the upper limit, and what's the lower limit? Is 0. Yeah, so we're sweeping, so theta goes from here to here just to get that portion of it. Okay.
Then it goes from where?
0 from here
Yeah.
to here, to pi over 4. Because if the slope is m, tangent of theta is equal to m. That's how you get it in general. Tangent of pi over 4 is equal to 1. Okay, so this is page 96 to 97 where that's worked out. Okay, we're done. We'll continue with this on Wednesday.
How did we, that's what we.
Wait, how do we know of this?
How did we know that shaded area was here?
Well, just because we know from these boundaries we know it's contained between these two spheres, and then from these boundaries we know it's contained within here.
Oh, yeah.